As we consider polynomials as functions, it's imperative to also to learn about intercepts and turning points as far as polynomials as functions are concerned. So, by way of introduction, we know that for a polynomial function f of x, intercepts tell you where the graph meets the coordinate axis. We've looked at this in some other direction. So we also have the idea of turning points, which tell you where the graph changes direction from increasing to decreasing or from decreasing to increasing. Then the pattern of intercepts and turning points together with end behavior actually gives a strong qualitative picture of the graph of y equals f of x. That's now considering a polynomial as a function. So a concept we had seen previously is that of y. I mean, we've seen x-intercept a lot, but now let's look at y-intercept, which we've also been saying without actually talking about it so much. The y-intercept is where the graph crosses the y-axis. Okay, so on the y-axis we have x equals 0. On the y-intercept is the point 0, comma f of 0, right? So for a polynomial f of x equals an x raised power n plus an minus 1 x raised power n minus 1 plus all of that up to plus a1x plus a naught. We have f of 0 to be a naught. That is, if you put x, if you put 0 for x, right? Every other thing evaluates to 0 apart from the constant. So f of 0 is equal to a 0 is sub 0. So the y-intercept is simply the constant term a naught, usually. So graphically, we can plot the point 0, comma f of 0 to get one fixed anchor point on the graph. So, I mean, that's a wise way to even start. If you want to plot a graph without, maybe you don't even have a tool like an app to use like Desmos that I always use. So you can already get a sure point on the curve, by just substituting x equals 0. So there you get the y-intercept. Okay. So of course, before now we already have a clear idea of what x-intercepts are. So the x-intercepts, also called roots or zeros, are where the graph crosses the x-axis. So on the x-axis we have y equals 0. So I mean, this is at the risk of talking without you seeing what I'm talking about, let me go to Desmos and do a bit of demonstration. Okay, now this is, let's say we have x squared, okay, minus 5x minus 2. Right. So if you put 0 in this, right, if x is 0, you automatically have the expression to be minus. You have minus 2 left, which is the y-intercept that we talked about the other time. So you see, this is exactly the point where the graph cuts the y-axis. On the other hand, the point where this graph cut the x-axis are these 2 points now, which also serve as the solutions of the graph. That's minus 0.37288 and 5.37228. Right. So this is y-intercept right here, and these are the x-intercept, which are the zeros or the roots. Okay. For the graph y equals f of x, this means that f of x equals 0. So when f of 0 gives you the y-intercept, while f of x equals 0 gives you the x-intercept. So to find the x-intercept, you solve the equation f of x equals 0. So each real solution, x equals r, gives an x-intercept that's r, comma 0. So for a polynomial of degree n, it has at most n real x-intercepts, and it has exactly n complex roots, counting multiplicity, but not all must be real, right? So if, I think we've talked about this in previous videos, talking about a rule about multiplicity of roots. So if f of x is a into x minus r1 raised by m1, x minus r raised by m2, all the way to x minus r k raised by mk, where Ri are distinct roots and Mi are the multiplicity, then the x-intercepts are the real Ri. Each real Ri appears as a root with multiplicity M sub I, like we've been saying before now. So turning point definition since here we're talking about intercepts and turning points. So we've now talked about intercepts. So we have y-intercepts where if any curve you have crosses the y-axis, and uh then for the x-intercepts where the curve crosses the x-axis. And those also serve as the roots or the zeros of the function. So a turning point of a function y equals f of x is a point on the graph where the function changes direction. Okay, so you have local maximum, the graph changes from increasing to decreasing, and you have local minimum, the graph changes from decreasing to increasing. So if you look at the same graph I have right here, so you see the graph here, it has three components. You have this portion up here, which is positive, and then it comes down here, and it becomes negative. So from negative now it switches over and it turns from decreasing to increasing, and then it keeps increasing. So all this branch that it's decreasing, then the turning point is where it changes course and it increases. That is when you have a minimum point now. So you see that a local maximum of a local minimum is for the local minimum, the graph changes from decreasing to increasing. Now, there's a very simple trick. I mean, from previous examples, there's a simple trick you can do here to change it to something that has a local maximum. So this is a local minimum right now, right? But if I just change the coefficient of the leading coefficient, if I change it to negative, this automatically flips over, and then it has a maximum point where it now changes from increasing to decreasing. So this is what you can now call the local maximum. So formally, at a turning point, we see that x is equal to c. So at a turning point, the x is equal to c, and f is defined near c. So for smooth functions like polynomials, we typically have f prime of c is equal to 0. So for polynomials, right? So this point, you can easily get it by differentiating this expression, minus x squared minus 5x minus 2, and equating it to 0. It will give you this point, which is minus 5 over 2, then comma 9 over 4. I mean, we can actually practicalize that. So you want to get that maximum or minimum point. You differentiate at this point and substitute 0. No, substitute a particular value c, right? So the sign of f prime of x changes as x increases through c. As x increases through c, the derivative changes. The sign of the derivative changes. Okay, now we are gradually moving, and then we'll get to that point where we actually find turning points like that. I have done this, of course, under basic calculus, but I think this is good again to consider under polynomials. So for a polynomial f of x of degree n, the derivative f prime of x is a polynomial of degree n minus 1. So turning points occur at critical points where f prime of x is equal to 0. So, I mean, there's a lot of information coming right now. We have f of 0 equals 0, which gives us y-intercepts. We have f of x equals 0, which gives us the x-intercepts. But then we now have f prime of x equals 0, which gives us the critical points, or which you can call turning points. So where turning points occur, since polynomials are differentiable everywhere, polynomials are differentiable everywhere. They are not like rational functions, which will not have derivative at some particular values. Then procedure, compute the derivative f prime of x. So if you want to find turning points now using the derivative method, so you compute the derivative f prime of x, solve f prime of x equals 0 to find critical values x equals c. Then each real solution x equals c is the candidate for a turning point. Then check the sign of f prime of x around c. So if f prime changes from plus to minus, then f has a local maximum at x equals c. If f prime changes from minus to plus, then f has a local minimum at x equals c. Okay, so if the sign of f prime does not change, then x equals c is critical point but not a turning point, e.g. it is a flat inflection point. We are going to see all of this in action as we move on. Okay, so let's talk about maximum possible number of turning points. So we already know the maximum possible number of roots which we know is equal to the degree of whatever polynomial you're solving. So for a quadratic polynomial, for instance, the maximum roots will be 2. But for turning points, the case is different. The maximum number of turning points would usually be 1 less the degree of the polynomial. All right. So let f of x be a polynomial of degree n. Then f prime of x is a polynomial of degree n minus 1. So a degree n minus 1 polynomial has at most n minus 1 real roots, right? Therefore, um, f of x have at most n minus 1 turning points. So, um, so examples now. For degree 1, which is linear, we know y equals ax plus b. This one has no turning points, right? Because it is linear. But degree 2, which is quadratic, y equals ax squared plus bx plus c. It has at most one turning point, which is the vertex, right? So, I mean, for degree 2, now this one is of degree 2, and it has only a single turning point, as you can see right here. Or if you make this one positive, that turning point was maximum. Now it will be minimum here, like that. So, at most one turning point, which is the vertex. Degree 3 is cubic, which has at most 2 turning points. Imagine if I just change this power to 3, you see it clear that we have a maximum point here, and we have a minimum point right here. So it's a degree 3. It has 3 roots as expected, right? And then it has 2 turning points, one maximum point and one minimum point, like that. So, of course, if you change this one to negative, we can have a kind of flip over. Okay, you see it now stretches out like this. So you see, I suspect that what is happening here is that we have multiplicities. We have multiplicities. Or if you center it, now you just see everything stretching out forever. So we have multiplicities, or it's either we have multiplicities or we have uh complex. Imagine some of the roots are imaginary. That's what I see there, because we only see one real root right here. One real root or two real roots that are multiple, or one real root and the rest are complex, or uh one real root with a number of multiplicities. One, maybe some others are complex. So for degree 2, we have at most one turning point. At most one turning point. Degree 3 is cubic. And then we have at most 2 turning points, just like I've demonstrated there. Degree 4 is quartic, and we have at most 3 turning points. So all I just need to do here is change this one to power 4. And then, of course, so we say it has at most 3 turning points, right? But here we can see that two of the and here we see that it shows only one turning point, because probably we have some imaginary results. So if I remove the negative sign, so it still has one, it still has one, because we have some complexities involved, most likely, or multiplicity if possible. Okay, so the actual number of turning points may be less than n minus 1, right? So if you have something of degree n, the actual number of turning points is that you can have at most n minus 1 turning points. But from what we've seen generally, the actual number of turning points may be less than n minus 1, depending on the specific coefficient of the polynomial. So the coefficients actually matter in determining the number of turning points. So let's talk about multiplicity of roots and local behavior. I mean, we've talked about this in a sense in a previous video, talking about multiplicity itself, and then we saw n behavior. So suppose x equals r is a root of f of x with multiplicity m, meaning that f of x equals x minus r raised by m multiplied by some g of x, where g of r is not equal to 0. So the multiplicity m tells us how the graph behaves near the x-intercept r, 0, right? So if we can have a simple root where we have just multiplicity of 1, so the graph crosses the x-axis at x equals r, right? So x equals r being the root, like we said already. So for instance, let's start with something. Okay, let me just go back to where I started from. Maybe just a simple quadratic expression like this now. So this one, we have the two roots here. All the roots are real, as we can see, and we have just we have a single turning point, which is a minimum point, by the way, right? So and each root has multiplicity of 1. So the graph crosses the x-axis at x equals r. So so the r here is minus 0.37288 for this first one. For the second one, the r here is 5.37228, right? So the graph crosses at those 2 points. So the sign of f of x changes as x passes through R, of course. So it's coming here. So as so we have it's coming. So for this up part now it's positive, okay, and then by the time it passes through this, it becomes negative all this way. So this whole region is negative, and then by the time it passes through the other R here, it goes up positive again. So you see the signs are changing uh through those routes. So locally, it looks like a slanted line crossing the axis. Of course, you can see slanted line crosses the axis here, and then another slanted line crosses over. Okay. So if we have this is for simple root now. For even multiplicity, now I think the easiest way to handle even multiplicity will be something like maybe I have so I just come here. I know that maybe I now have x plus 1 raised to power 2. So you see, this is one solution occurring twice. So for even multiplicity, you see what happens there. This one just touches the curve at that point. Of course, I can go ahead and still multiply it by another factor, x minus 1. Okay, so you still have your even multiplicity right here. That minus 1 occurs here twice, but then we have another one which is plus 1, so we have minus 1 occurring twice here, and then we have minus 1, which is just once. So you see this one where it occurs twice, the graph just touches there, and then for this one that is only one, the graph crosses over, just like in the previous case we considered, right? So let me center it. Yeah, so it's like that. So for even multiplicity, m even, e.g., m is 2, 4 and all that. The graph touches the x-axis and turns back. So that's what exactly we're talking about. So if I remove this part now, the graph touches and turns back. But then because we have this, the solution to this is -1 with multiplicity of 2. So it touches and turn back, but then if it is multiplicity of that is odd, like we saw before, so it crosses over, right? So the sign of f of x does not change across x equals r when you have even multiplicity. So you see the sign. So the graph was negative. It touches here and it just turns back to negativity. Except that now, of course, if I remove this now, you see it more clearly. So the graph is positive here. It touches here and it continues. It turns over and becomes positive again. It doesn't ever cross over to the negativity side of things, right? So near R now. So near R, we see that, I mean, the sign of f of x does not change across x equals r. We've seen that. Near R, for m equals to, it looks like a U shape, similar to y equals x minus r squared. Okay. Then for larger even m, it becomes a flatter U. So, but as we increase the power, as far as it is even, if you increase the power, it becomes like a bowl. This one it's like a parabola. So if I make it 4 now, it becomes like a flatter bowl. Make it 6, it's flatter again. Make it 8, it's even flatter. Okay, maybe we don't see it better this way. So we have the parabola to start out with. So if I create a function and then the power is now 4, you see it becoming flatter. I have this now. It's now 6, it's flatter. I have this now. It's 8, it keeps going flatter and flatter, basically. Okay. So often x equals r is a local minimum, maximum or local minimum, depending on the overall shape. So here now, it's local minimum, but okay, if I make this minus, yeah, it automatically flips everything over. If I make it negative here, flips everything over automatically, right? So now we have local maxima. Okay, so then talking about odd multiplicity, that is, the multiplicity is greater than 1, but odd. We already know what 1 is about. So for power 1, we just know there's no turning point, but we can get a root in that case. So imagine for x plus 1 raised to power 1, or simply x plus 1. So, you just have x plus 1 like this. So that goes. But if you just have minus now, it changes course, basically. So x plus 1, we have this. But what if we have odd powers that are not 1, like 3 at least? So you see what's happening. The x plus 1 is raised to power 3. Of course, this one has, the solution here is -1 with multiplicity of 3. So you see that -1 right here, So let's talk about that. So the graph still crosses the x-axis at x equals r in that case. So you can see at -1, which is the solution here, the graph still crosses the x-axis, but then the behavior is a little different. So the sign of f of x does not change across x equals r. So you see the function, uh, so you have the function coming, it's more like negative here, and then it goes positive. About the sign of f of x does not change across x equals r. So you see it's like you have a bit of slowing down around this point. Okay. Then the crossing is flatter or more S-shaped. So you see, it looks like you're writing some kind of S like this. So you have this flat thing, and then you have this smooth transition going that way. Okay, the crossing is flatter or more S-shaped. So for m equals 3, near r, the graph resembles y equals x minus r cubed, which flattens at the x-axis. So for a higher odd m, the flattening is even more pronounced. So now you see the sign remains here, like nothing is going to happen except that after a bit of time that happens. So if I do what I did like the other time, I now have other odd multiplicities, like this is now 5. So it's the same behavior, but that it's now smoother. So x is 7, like that. Okay. So of course I can also go negative, like if I now have this minus like this, you know, minus flips it over, minus flips it over, and then you have the flatness increasing as the powers, as the multiplicity, the odd multiplicity increases. Okay, now we can summarize now for multiplicity versus behavior at the root. So let x equals r be a real root of multiplicity m. So if m is odd, if m is odd and m is equal to 1, the graph crosses the x-axis. Okay, so we can so we have demonstrated that a whole lot. So imagine we just have a simple case of x plus 1, into x minus 1. Okay, so we have this just crossing single multiplicities, just simple like that. Okay, so crossing is relatively sharp like a line. So it just goes, just touches and moves on like that. Then for m, when m is other, m is greater than or equal to 3. Okay, so you have say in this case now you now have power 3. Okay, so you see this one behaving in a sluggish way, whereas this one is still sharp. For x, if you solve this, x is equal to -1 3 times, and x is equal to 1 1 time. Because x is -1 3 times, you have this slowing down happening. And then when x is equal to 1 once, so it just crosses once as it is. Okay. Then what else? M is odd, but m is greater than or equal to 3. So in this case, oh yeah, I've demonstrated that already. Okay, so for m even, so the graph touches and turns at the x-axis. There is no sign change in f of x. Often corresponds to its one turning point at the x-axis. So imagine here now, I now have this is raised to power 2. Okay, so you see this one is behaving sluggish like here because there's odd multiplicity for x equals -1. For x equals +1, which is now even multiplicity. So you see it touches and keeps moving like that. Okay, so we have all of that. Let's go ahead and see a systematic sketching using intercepts, turning points, and multiplicity. So to sketch, interestingly, this is going to end on this note, but the next video is going to talk about how to sketch graphs systematically. So systematic sketching using intercepts, turning points, and multiplicity. To sketch the graph of a polynomial y equals f of x systematically, so you can have degree and leading coefficient. So that's the first thing you want to look at. So determine the degree n and the leading coefficient an. These two are very important in what you want to do. So use this to predict n behavior. So what happens as x approaches plus or minus infinity? Note, at most n has real at most n real x-intercepts, and at most n minus 1 turning point. So if the degree is n, so you have that number of intercepts at most, then we have at most n minus 1 turning points. That is one less the number of intercepts. Then find the y-intercept by computing f of 0. Then plot the point 0, f of 0. Then find the x-intercept. Then solve f of x equals 0 exactly if possible or approximately. Then identify the roots r sub I and their multiplicities m sub I. Then plot r sub I, comma 0 for each real root. Then use multiplicity to predict local behavior at each root. So now we know what multiplicity looks like. If it is only one, it is sharp. If it is two, it touches and turns. If it is three, it changes over sluggishly. Then as the odd multiplicity increases, it begins to the sluggishness is flatter. And for even multiplicities, right? You have that touching and turning, which becomes flatter and flatter as the powers increase for even multiplicity. So use multiplicity to predict local behavior at each root. So decide where the graph crosses the x-axis. That's odd multiplicity versus where it touches and turns, even multiplicity. Anticipate flattening at roots of higher multiplicity, right? So those information will really help a lot. Then compute f prime of x and solve f prime of x equals 0. So for each real solution, x equals c, compute f of c and plus c comma f of c. Okay, so use the sign of f prime of x on either side of c to classify each as the local maximum, local minimum, or non-critical turning point. Then finally, you combine all information, you plot intercepts and turning points, connect them with a smooth curve that matches the correct end behavior. Okay, then the correct behavior at each root, that is crossing or touching, the maximum number of turning points, which is less than or equal to n minus 1. This gives a consistent qualitative graph of the polynomial. So we're going to do that fully in the next video. But before we go ahead and take care of all that, I'll solve this one question so that I can drive all the points I've been saying, so I can actually drive them home. Okay, yeah, I don't want to sketch graph here, by the way. Let me see if I can just get. Okay, nice, no problem. I'm going to do whatever I need to do with this one question. It says, consider the polynomial f of x equals 2x cubed minus 3x squared minus 11x plus 6, right? So find the y-intercept. I mean, that's easy peasy. Just put f of 0. So A, we need the y-intercept. B, we need to factor f of x completely. We already know how to do that. Factor f of x completely. Then finally, we now need use the x-intercept and y-intercept, make a rough sketch. Okay, we can do that. Make a rough sketch. Make rough sketch. Okay, though the sketching is coming fully in the next video, but I'll do that here too. So let's go to the worksheet and practicalize all the things we've been learning. Okay, so first of all, we have the function to be f of x equals 2x cubed minus 3x squared minus 11x plus 6. Okay, so the first question is to find the y-intercept. So to find the y-intercept, that's the first thing we're expected to do. To find the y-intercept, you know, so we can say it occurs at f of 0. Okay, so y-intercept occurs at f of 0. So, and we say f of 0 equals 2 into 0 cubed minus 3 into x squared minus 11 into 0 plus 6. Of course, we know all of this is gone, right? So that f of 0 is equal to 6. All right, so the y-intercept is 6. So easy. Then the next thing, we are told to factorize completely. Okay. So question 2. The next thing, to factorize f of x completely. Okay. That's the next thing. We've done this a couple of times. Now we already can know what the solutions are. So the leading coefficient, so here we are applying the rational rule theorem. Leading coefficient is A3, because the highest degree, the degree is 3. The leading coefficient is A3, which is equal to 2, and the constant is A0, which is equal to 6. So the uh the possible roots are factors. The possible roots are factors of they are factors of a naught all over an. Okay, a naught is 6, an is 2. That is equal to 3. All right. So the possible roots are factors of 6 over 2, which is equal to 3. So the possible roots are factors of 3. And that tells us that we have possibly plus or minus 1 and plus or minus 3. So the solutions, so I mean, this is a very scientific way of looking for these roots now. So we know that whatever the roots of this expression are, it cannot get out of this 4. It has to be either plus 1 or minus 1, plus 1 or minus 3. And that's good for us, right? So we can go methodically to find those roots now. So since we already know, we're not sure that any of them will be, at least we know if there's going to be, if this solution may not be factorizable, by the way. But if it is factorizable, we know that the possibilities will be around plus 1 minus 1 plus 1 minus 3. So then we can try to find the first factor, to find the first factor. Okay. Then we begin the try thing. Try f of 1. Try f of 1 means that okay, try x equals 1. Okay, so we're assuming want to try if x equals 1 is the root of the expression of f of x. So we now have f of 1 to be 2 into 1 cube minus 3 into 1 squared minus 11 into 1 plus 6. So this is 2 minus 3 minus 11 plus 6. So for the negatives now, we have minus 14 and 2 plus 6 is 8. So 2 minus 3 is minus 1. Okay. Minus 1 minus 11 is minus 12. Minus 12 plus 6 is minus 6. This is not equal to 0. So x equals 1 is not a root, and x minus 1 is not a factor. It's not a factor. It's not a factor of f of x. Okay, so that ends at that. Then we can then try minus 1. That's another possibility. So what this one helps you to do is that you don't try anything outside of this. You don't waste your time trying anything that is not a possibility. So again, now what we now try x equals minus 1. Okay, try x equals minus 1 so that f of minus 1 is equal to 2 into 1 cube. 2 into minus 1 cube minus 3 into minus 1 squared minus 11 into minus 1, okay, plus 6. So we have 2 into minus 1 minus 3 into 1 minus 11 into minus 1 plus 6. So this is minus 2 minus 3 plus 12 plus 6. Okay, so this is minus 2 minus 3. That's minus 5. Minus 5 plus 18. That's 13, right? That's 13. So 18 minus 5 is 13. Again, this is not equal to 0. So x equals minus 1 is not a root, and x plus 1 is not a factor, of f of x. I hope I don't there's no error here, right? I hope there's no error. 2x squared. Okay, let me see, because by now I felt that one of it should have worked. 2x cubed minus 3x squared minus 11x plus 6. Okay, I think we are good. Yeah, I mean, you have to keep checking like that so that you don't waste your time. Yeah. So again, so that means these ones are ruled out. So these ones are ruled out. So we can check plus or minus 3 now. Okay. So plus or minus 1 gone. So again, we try x equals 3. So we try x equals 3 so that we have f of 3. That is 2 into 3 cubed minus 3 into 3 squared minus 11 into 3 plus 6. So that is, I'll just go straight here. 3 cubed. So 3 raised by 3 is 27 times 2, 54. Minus 3 raised by 2, 9 times 3, 27. Minus 33 plus 6, I think. So 54 minus 27 is 27. 27 minus 33. 27 minus 33 is minus 6 plus 6, 0. Yay. Finally, we have our result. So you can say that x equals 3 is a root, and x minus 3 is a factor, the factor of f of x. Okay, now that we have got a root, then we are good to go to factorize further. So now that we have this, we can then say to get the other factor, to get the other factors rather, using synthetic division, using synthetic division, using synthetic division. Okay. Again, let's remember where we are coming from. We know f of x is, we are considering polynomials as roots. 2x cubed minus 3x squared minus 11x plus 6. Okay. And the factor, which we can call the divisor now. Okay. I think that we usually call d of x, if you like. That is x minus 3 now. That's what gives us 0, you know. So x minus 3. So using synthetic division, all we just need to do is write out the coefficients. So for x cubed, we have 2. For x squared, we have minus 3. For x, we have minus 11. Then I usually like to write this one last and put the barrier, because whatever we get is going to tell us if it's a factor or not. Already we know it's a factor, right? And then from this x minus 3 now, that's x equals 3 if we equate to 0. All right. So it means we write this 3 here, and then we try to get the other factors, we now go this way. So this 2 now, you drop it first of all. So you have 2 here, then 3 times 2. 3 times 2 is 6. Okay. So minus 3 plus 6 is 3 right here. Okay. So next you have this 3 now times 3, that is equal to 9. Minus 11 plus 9 is minus 2. Okay. Then lastly, we have again 3. Okay, let me do the color separately to be sure you get it. So 3 now times minus 2, that's minus 6. 6 minus 6 is 0. So because we have 0 here, it tells us that actually x minus 3 is a root of that polynomial. But the catch, this is the catch now. The catch is that this coefficient, multiplying this by x raised power 0, x raised power 1, x raised power 2, will give us the other factor. Okay? And so the other factor, the other factor is 2x squared plus 3x minus 2. Okay, this is the other factor. All right. So to remind yourself, you can then say we can write f of x equals 2x cubed minus 3x squared minus 11x plus 6, is equal to the first one, x minus 3 into 2x squared plus 3x minus 2. Is that really plus 3 or minus 3? Yeah, it's plus 3. Good. So we can then factorize this completely. Okay. So I'll just do it all in one place. So this one now is quadratic, so it can be easily taken care of. And then we know that so for this quadratic part now, we have we can use the AC method here because x squared has a coefficient and we have the constant. So if you multiply 2 times minus 2, this is A now and this is C. Okay, 2 times minus 2 is minus 4. And then B, which is in the center, is 3. So we need two numbers. We multiply to get minus 4, and then we add to get 3, right? So easily, I believe those two should be, they should be factors of minus 4. And because we need 3 here, I believe it should be 4 times minus 1. 4 times minus 1 is minus 4. 4 minus 1 is 3, which we need. So we can then say, so since all of that is in place now, so we can write this that, okay, let me even remove this. So we can then come here and say this is 2x squared. Then 4 and minus 1 is what we have. 4 minus 1. So plus 4x minus x. That's minus 1x is minus x minus 2. So here now, 4x minus x is the same thing as 3x. And then we can move on like this. So we have x minus 3 into, so we can group now. So we have 2x squared plus 4x minus x plus 2. Because we have minus in the middle, so the other sign changes. So we have x minus 3 into into we can factorize, and we have 2x into x plus 2 minus 1 into x plus 2. Okay, so we now have x minus 3 into x plus 2 into 2x minus 1. Okay, so so that gives us, so for the fact now we have f of x has been factorized completely now. So these are the factors. um then then the roots of f of x are x minus 3. Okay, we can say x, just equate each one to 0. The roots of f of x equals 0. If you equate to 0, are x equals 3, x minus 3 equals 0. That will give you 3. Then x equals minus 2, or x equals 1 over 2. Okay. From what we had before, right? We have so for rational roots, how come I escaped this other one? So a naught over n, yeah. The fractional part is not here, but that's okay. At least we got the big ones. So x is 3. Something is wrong. What is really wrong here? This is 6 over 2, right? Plus or minus 1, plus or minus 3. Mm, okay, that's my fault. That's my fault. I think I didn't do this right in the beginning. So I think what we should do is so you look at all the possibilities here. Yeah, very important. Look at all the possibilities here. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And here, we look at all the possibilities, plus or minus 1, and plus or minus 2. And then the solutions, the possible solutions. Okay, got it. Possible solutions. That's my bad. Possible solutions will now be each one over each one. Okay, so plus or minus 1 over plus or minus 1, that's the possibility, plus or minus 1. Then plus or minus 1 over plus or minus 2, that's plus or minus 1 over 2, sorry. Then plus or minus 2 over plus or minus 1, that is plus or minus 2. Okay, that's my problem. Then plus or minus 2 over plus or minus 2, that's plus or minus 1 already. Plus or minus 3 over plus or minus 1, that's plus or minus 3. Then plus or minus 3 over plus or minus 2, okay, you have plus or minus 3 over 2 again. Then plus or minus 6 over plus or minus 1, that is plus or minus 6. Then plus or minus 6 over plus or minus 2, that's plus or minus 3 already. Okay, so these are the possible solutions. Sorry, that was my bad. I should express them separately. So we have a larger space. And then you see all these solutions, what exactly we've got here. Yeah, so please pay attention to that. Or you can revisit the rational roots theorem video to verify. So now we have got the all the possible roots in this case. Okay. So the last thing we need to do is to sketch the curve, which I think I'll probably delay. But since we also talked about turning points, so we can now verify. So to verify, to verify, to verify the nature of turning points, okay, what we learned is that turning points occur at f prime of x equals 0. Okay. So here now you have f of x, is f of x is equal to 2x cubed minus 3x squared minus 11x plus 6. And you know f prime of x is simply differentiating 6x squared minus 6x minus 11. Okay? So, I mean, normally if you solve this, we should get the turning points. Okay? So, f prime of x equals 0 is 6x squared minus 6x minus 11. So we can use the AC method. Okay. What I should say is, for turning points, I think I need to switch over. So, for turning points, 6x squared minus 6x minus 11 is equal to 0. So here now, because it's degree 3, we have got 3 roots, but the turning points we are going to have maximum of 2. So which we are going to get from this quadratic expression. So using AC method now, 6 times minus 11 is minus 66. So we need two numbers to multiply to get minus 66. And we add to get, so you need m plus n equals, we need mn. We need mn equals minus 66. And we need m plus n. We need the same m plus n to be minus 6. So clearly that should be 11 times 6. And because, no, is it 11? No, it can't be 11 times 6. Minus 66, right? There should be factors of 66. Is this going to work? Let's see. Okay, let's use the formula method. Okay, let's use formula method because this one is looking like it may not work. 66, yeah. 11 and 6 is not working for sure. So, using the quadratic formula, okay. So we have A to be 6, B is minus 6, and C is 11. So we have X to be minus B plus or minus square root of B squared minus 4AC all over 2A. So X is minus B, that's minus 6 plus or minus square root of minus 6 squared minus 4 into 6 into 11 all over 2 into 6. So X is 6 plus or minus square root of 36 minus 24 times 11. That's minus now. That's minus 24 times 11. That's 264 all over 12. Okay. So obviously, we are going to have complex roots here. Okay. So I think I'll stop there for now because of the complexity. So just know that there are no real roots, and I'll just stop it there. But one more thing we can do is to see, we'll just look at what the graph looks like on Desmos, and we stop with that. So I come over here now and say this is 2x raised to power 3 minus 3x raised to power 2 minus 11x plus 6. So here now, yeah, we surely have some turning points. Minus 0.9 something something. We have a maximum point and a minimum point. But why is that not working here? It should work. Because this is 4 minus 4 AC. So it's imaginary. There are no real roots, but we have real roots. I suspect. Okay, there are no real roots for this particular expression. Let me see that. 6x squared minus 6x minus 11. 6x squared, 6x squared, 6x squared minus 6x minus 11. They are real roots now. Oh, I think it's my problem somewhere. C is minus 11. Yeah, C is minus 11. My bad. C is minus 11 right here. Sorry. So this is minus 11. So they are real roots for sure. So this is simply plus this. So, okay. Yeah, they are real roots. Sorry. So you see, that's why we need to be able to check these things. So x is 6 plus or minus square root of 36 plus 64 is 100, I think. So that should be root 300 all over 12. I think so. Yeah. Yeah, root 300 over 12. So x is 6 plus or minus roots. Okay, I mean, I think we just need to get root 300 out now. Okay, or better still, I think it's easy to factor these things out here. Like, okay, so we have this is root 100 times 3, in case you don't even have a calculator, divided by 12. So this is x, 6 plus or minus 10 root 3 all over 12. Okay, so x is equal to 6 plus or minus root 3 is 1.73 to 1.732 all over 12. So we have x to be 6 plus or minus 10. That's 10 times 1.73. That's 17.32 all over 12. Okay. So x is equal to, so we have it in two ways now. We can have we have 6, that's 6 plus 17.32 divided by 12. So that's 1.94 1.9433, or x is equal to 6 minus 17.32. That's minus 0.94 minus 0.9433 minus 0.9433. Okay, so these are the deals. So these are the turning points. Then we can then go further and verify, but we are going to do that in the next video. So let me now keep on with this. So finally, now we see that the expression 2x raised to power 3 minus 3x raised to power 2 minus 11x plus 6. 2x raised to power 3, 3x raised to power 2. Okay, so see what we have now. So we have 3 roots, minus 2, 0.5, and 3. And those are the results we got initially. Okay, so those are the results we got initially. That's okay, 3 minus 2, 0.5. Okay, we got that. And then we have 2 turning points. We have a maximum point and a minimum point. So most likely this is the, okay, we can't be sure. We can't be sure from the graph, but I mean, we could have, there's a way to test for that, which we are going to talk about in the next video. So here now we have, so look at this now, we have x is, so at this point now, minus 0.94338, right? That is the maximum point. This is the maximum point. So this corresponds to the maximum point, and this corresponds to the minimum point. For minimum point, we have minus 0.9433. 1.9433. That's the minimum point, which we have right here. This point now. 1.9433, like that. Okay. So with this, we come to the end of this video. It's been a very lengthy one. Thanks for listening. Let me know how helpful this is for you. And there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I must thank you very much. If you haven't subscribed, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Okay. Having done that, you can become a member of the channel by clicking on join. Ultimately, don't forget to comment, like, and share. Bye.